Welcome to Kanerika's podcast, The Digital Shift. So let's start right off with a number that should make every technology executive sit up and take notice. Right now, in 2026, 71% of data leaders are actively worried about hallucinated or incorrect data reaching their stakeholders.
Yeah, that statistic really highlights a fundamental breakdown in modern architecture.
Mhm.
Because, when you look closely at why that is happening, you realize it is rarely a pipeline issue.
Right.
Most data problems, whether they surface as a broken executive dashboard or worse, an AI agent confidently giving a completely wrong answer to a CEO, they start a layer deeper. They actually start in the data model.
I mean, a pipeline can be perfectly clean, and the cloud warehouse can be lightning fast. But if an AI agent is sitting directly on top of a sloppy schema, well, the whole system just collapses.
Exactly. The AI agent doesn't have the inherent tribal knowledge of a human analyst who has been at the company for 5 years. It only knows what the structural foundation explicitly tells it.
Which brings us to the mission for today's discussion. We are exploring the real-world impact of modern data modeling best practices that actually drive results. We are going to cover how to design for the questions the business is actually asking, how to choose the right structural techniques, and how to govern effectively.
That is the core of it. The ultimate goal is to understand how you integrate AI seamlessly without getting dragged down by the legacy mistakes of the past decade. Because honestly, disciplined modeling is what actually drives results.
So if you are listening to this and wondering why your AI initiatives keep stalling, the reason it hallucinates is so often because the data was modeled for the source system, not the business.
Yes, exactly.
I look at building a data model purely from source systems like, well, it is like building a house based purely on what the local lumberyard happens to have in stock today, rather than what the family actually needs to live in. You just end up with a structure that reflects the inventory, not the inhabitants.
That lumberyard comparison is spot on. The solution to that mismatch is a discipline known as decision intelligence. Rather than looking at the raw data you happen to have, you work backward from the recurring business decisions your stakeholders actually make.
That makes perfect sense.
Take a retail finance team, for instance. They are likely asking for margin by region and week. But a customer support team down the hall is asking which specific accounts are at the highest risk of churn. Those two questions require entirely different analytical structures to answer efficiently.
So before anyone even opens a modeling tool, you have to rank those decisions by frequency and business impact. I mean, you prioritize the questions that get asked every single week over the obscure one-off requests. And crucially, you have to define the grain.
Oh, defining the grain is where so many projects fail before they even begin.
Break that down for someone who might not be in the weeds of database architecture every day. What does defining the grain actually look like in practice?
Well, the grain is simply the level of detail a single row of data represents. Like, is one row going to represent an entire customer account? Or is one row representing a single line item on a specific order placed on a specific day?
Right.
You have to nail that down explicitly. Because if you mix grains, like having daily sales targets in the exact same table as individual transaction receipts, your aggregate math will be completely wrong. Your reporting tools will literally double count revenue.
And once you understand those questions and define that grain, you have to translate those requirements into entities. But the trap here is naming those entities after the source tables.
Right, the technical debt trap.
Exactly. Because if you name an entity Table Cuss Arrow 2 just because that is what your legacy CRM system happens to call it, you are baking technical debt directly into the analytical layer.
Just think about what happens when you migrate to a new CRM 3 years from now. That technical name, Table Cuss Arrow 2, becomes completely obsolete.
Yeah.
But you are stuck with it because it is hard-coded into 100 different downstream reporting layers.
Which is a nightmare to untangle.
Absolute nightmare. The best practice is to keep one canonical definition per business concept. You name the entity customer, or you name it contract. That ensures the entity name survives any future source system migration. It essentially aligns the engineering architecture with the actual business process.
So if starting with the business questions is the what, we really need to transition into the how. Once you know what the business is asking, how do you structure it physically? Because there certainly isn't a single correct data modeling technique in 2026.
No, not at all. It depends entirely on the workload you're trying to serve. Let's look at the three major techniques dominating the landscape right now. The first is dimensional modeling. For business intelligence and reporting tools like Microsoft Power BI or Tableau, dimensional modeling remains the absolute gold standard.
Those are your classic star or snowflake schemas, right?
Exactly. They organize data into central fact tables containing the numbers you want to measure. And those are surrounded by dimension tables containing the descriptive context, things like time, geography, or product details.
They are incredibly fast to query and very intuitive for business users to grasp.
They are. If your metrics are stable and your primary goal is fast aggregations for executive dashboards, well, dimensional modeling is still the undisputed champion. But if you operate in a highly changeable or heavily regulated environment, like banking or insurance, a standard star schema might not provide the historical tracking you need.
Which is where data vault modeling comes in. Data vault is so interesting because it splits the data up in a very specific way.
It splits data into hubs, links, and satellites. Hubs represent the core business keys, links represent the relationships between those keys, and satellites track all the descriptive attributes and historical changes over time.
So it handles changes really well.
Beautifully. The mechanism here is that it handles schema drift gracefully. If a new source system is added, you just attach new satellites and links without breaking the existing model. It provides exceptional auditability because every single historical change is captured and time-stamped rather than overwritten.
Which brings us to the third major technique, and honestly the one causing the most data right now, the one big table, or OBT structure. This is essentially a massive, wide, completely denormalized table.
Yes, the rising star.
We are seeing this become the go-to for AI and semantic layers using platforms like Microsoft Fabric or Databricks. But wait, I have to challenge this.
Go for it.
Doesn't building a one big table destroy the fundamental discipline of data normalization? Aren't we just creating a massive, messy spreadsheet and abandoning decades of relational database theory?
It is the most common pushback we hear from veteran database architects. But to understand why OBT is used, you have to look at the mechanism of how large language models actually process information.
Okay.
An LLM predicts the next logical word or token based on probability. When you ask an AI agent a question and it has to navigate a highly normalized star schema with 15 interconnected tables, well, the probability of it writing the SQL join path correctly drops drastically.
So the AI just gets lost in the maze of relationships.
Precisely. It loses context, it joins the wrong keys, and boom, you get a hallucinated number. By flattening the data into a wide, denormalized one big table, you drastically reduce the join complexity. The AI only has to look in one single place to find everything it needs.
That makes perfect sense for the machine.
But the critical clarification here is that a one big table is not a replacement for a governed normalized core. It is merely a serving layer built on top of it. Your underlying dimensional or vault model maintains the structural integrity and feeds that wide table for the AI to consume safely.
So the structure serves the specific consumption layer. You build the robust foundation and then project the wide table specifically for the AI agent. We at Kanerika see this transition firsthand when our clients outgrow their legacy systems.
Oh, constantly.
They suddenly realize their highly normalized on-premise databases simply cannot feed an AI agent quickly or accurately enough.
And when enterprises attempt to modernize that architecture, the transition can be incredibly daunting. Just the mapping alone can take months.
Right. And to accelerate that transition, we use our migration accelerator, Flip. By automating the discovery and mapping phases of these complex environments, Flip cuts the migration effort by 50 to 60% compared to a manual rebuild.
That is a massive time saving.
It really is. It takes a lot of the human error out of mapping legacy systems to modern cloud architectures.
But, migrating the data is only half the battle. Once you have successfully migrated to these modern structures, governance is no longer optional. Ambiguous data ownership is the top challenge for 41% of data leaders today.
That is a staggering number.
If nobody clearly owns a table, nobody updates it, nobody checks it for quality, and eventually that AI agent is serving stale or corrupt data straight to the executive team.
Governance really is the glue holding everything together, but manual governance simply doesn't scale. You mentioned standardizing naming conventions earlier. Whether an engineering team chooses snake case or camel case matters less than strictly enforcing that choice.
Exactly. Consistency is key.
So how do teams actually enforce this without grinding development to a complete halt?
You have to automate the governance checks directly into your development workflow. In software engineering, there is a concept called continuous integration and continuous deployment, or CI/CD pipelines. It is basically an automated process that tests code before it goes live.
And data teams are borrowing that.
Exactly. Data teams are now using CI/CD pipelines for their schemas. For example, you can configure the pipeline to automatically flag orphan tables, Or you can block a deployment entirely and send an alert if an engineer tries to add a new column without attaching a documented data owner to it.
So the system physically prevents the technical debt from ever being deployed. That makes a lot of sense. But governance also requires a semantic layer for the humans and the machines to understand what the data actually means.
Yes, the dictionary aspect.
Right. This is where building a usable, searchable data dictionary utilizing tools like Microsoft Purview becomes absolutely critical.
But a data dictionary only works if the definitions are written in business language first. The technical field name should just be a secondary reference. If someone looks up revenue in the dictionary and the definition just says it is the sum of the rev column, well, you have completely failed at governance.
Which bridges us perfectly into the paradigm shift of AI agents. Generative AI needs that business context just as much as a new employee does. I mean, an AI agent lacks tribal knowledge. It can't walk over to the accounting department and ask why there are two completely different customer IDs.
No, it cannot. It only knows what the governance and semantic layers explicitly tell it. And this is a major stumbling block for companies trying to deploy AI.
How so?
Well, generative AI cannot simply infer that a field called custod and field called customer number are the exact same concept in two different systems. A human analyst might look at the data in those two columns, recognize the pattern, and know they join together. An LLM needs a semantic layer to attach that concrete business meaning to the physical fields.
The metadata absolutely must be machine readable. It can't live in a static PDF document, a forgotten wiki page, or just in a senior developer's head.
Never.
But even with a great semantic layer, things can still go wrong. A model might look logically perfect on a whiteboard, but when a business user asks an AI agent a natural language question, the translation layer can break down.
Which is why testing with actual conversational agent queries is the only way to guard against silent hallucinations.
Let's talk about silent hallucinations because that sounds like a nightmare scenario. How do you catch a silent hallucination if the AI sounds perfectly confident and plausible?
It is incredibly tricky.
Right. Like if the AI says revenue is up 12% for Q3 with absolute authority, how does the end user know if the underlying query was actually correct?
It is the most dangerous failure mode in modern analytics because it degrades trust in the entire data apparatus. To catch it, you must establish strict guardrails within the semantic layer. You literally force the AI agent to explicitly cite its specific table and field for every calculation it returns.
Ah, so the AI has to show its work.
Exactly. By exposing the lineage of the answer alongside the natural language response,
Right.
you allow human operators to spot-check the logic immediately. If the AI claims revenue is up 12%, but the required citation shows it queried the projected pipeline table instead of the closed-won deals table, the human catches the error instantly.
It turns what is essentially a black box into a transparent, auditable process. That is brilliant. But, even with those guardrails, human errors during the physical modeling process compound at scale. If we look at the technical execution, what are the common pitfalls we have to avoid?
The first major mistake we see constantly is over-normalizing early. Teams get obsessed with textbook database theory and try to reduce every single piece of redundancy.
It's going way too far.
Yes. They end up multiplying joins to a point where it completely kills query performance in the cloud. You have to match the normalization level to the actual query patterns your users are running.
So it is like over-engineering the foundation before you even know how the house is going to be lived in.
Precisely. And the second common mistake is mishandling slowly changing dimensions, or SCDs. Real-world data changes all the time. Customers move to new states, product category shift, sales reps get reassigned.
Right, data is never static.
Exactly. So you have to know when to simply overwrite the old data, which is an SCD Type 1 approach, versus when to track the full history of those changes, which is an SCD Type 2.
Wait, let me make sure I'm wrapping my head around this. If you use Type 1 and just overwrite the old data, isn't that incredibly risky for historical reporting?
Very risky.
I mean, it is like a legal trial where a witness is allowed to change their testimony retroactively. You completely lose the true historical timeline of what actually happened.
That is a phenomenal way to visualize it. If a customer lived in New York last year, and they moved to California today, and you just overwrite their state in a Type 1 dimension, your historical reports for last year will suddenly show those past sales originating in California. You have essentially rewritten history.
And if you train a predictive analytics model on silently overwritten history, well, it is going to learn completely false trends because the past was erased.
You cannot predict the future. if your record of the past keeps shifting. This is exactly why knowing when to use type 2, which adds a new row for the change and keeps the old row intact with a timestamp, is so absolutely critical for AI readiness.
What about the physical code of the models? I imagine treating a schema like a static diagram rather than version-controlled code is a recipe for disaster.
It is. Skipping version control is the third major mistake, and this directly impacts the tooling landscape in 2026.
The tooling really has evolved dramatically to solve this. We are seeing a massive shift toward Git-based version control tools like DBT and Coalesce, especially for cloud data
Oh,
warehouses.
they are completely taking over.
Because these tools treat schema definitions as literal code. That means changes to the data model can be peer-reviewed, automatically tested in a staging environment, and rolled back exactly like application code if something breaks.
It brings software engineering rigor directly to data engineering. Conversely, for massive, highly regulated environments, we still see heavy reliance on enterprise governance-centric modeling platforms like Irwin Data Modeler or Idera Studio.
So how does an organization know which route to take?
The key is to match the tool to the team size and the specific structural technique. A nimble five-person analytics team trying to move fast will completely drown in the overhead of a heavy enterprise tool, just as a global bank will find a lightweight Git tool completely insufficient for their strict compliance and visual mapping requirements.
It all comes together when you see the tangible impact of doing this correctly in a real-world scenario, bringing the business questions, the structural techniques, governance, and AI readiness into a single cohesive strategy fundamentally changes how a company operates.
It changes everything.
We at Kanerika actually recently completed a major project that illustrates this perfectly. We migrated a client's semantic models from legacy SQL Server Analysis Services, or SS, directly into Microsoft Fabric.
That transition is a prime example of everything we have covered today. The client's legacy SS infrastructure was severely restricting their ability to collaborate in real time.
It was a massive bottleneck.
Manual updates on their existing semantic models were consuming massive amounts of engineering time every single release cycle. And on top of that, the tightly coupled legacy models were degrading query performance as their data volumes grew.
They were basically trapped by their own architecture. So, by using our automated transfer processes, we modernized their entire semantic layer. But the real game changer was leveraging Microsoft Fabric's Direct Lake mode.
Direct Lake mode is such a fascinating shift in how data is served. For those unfamiliar, instead of constantly moving and copying data from the warehouse into the reporting engine, which takes time and massive computing power, Direct Lake allows the reporting layer to read the files directly from the data lake storage without moving them at all.
It completely eliminates the lag. The statistics from that transition are just incredible to look at. By combining a better data model with modern serving architecture, we achieved a 25% increase in real-time analytics capability for the client.
Meaning the executives could finally see what was happening right now, not yesterday.
Exactly. Furthermore, we delivered a 40% reduction in manual maintenance effort. By fixing the structural foundation and the governance, we freed their data engineers to actually build new predictive features instead of just putting out fires all day.
That is a huge cultural shift for an engineering team.
And overall, we secured a 20% improvement in data integration efficiency. That is the true power of getting the data model right. It removes friction from every single downstream process.
It really does.
And frankly, this is exactly what we do. Kanerika was founded in 2015, and we are an AI-first data and automation consulting firm. We have partnered with over 100 enterprise clients, maintaining a 98% retention rate, and we hold elite partner status with Microsoft, Databricks, and Snowflake.
We basically help organizations ensure their data architecture isn't just a static storage locker for information, but an active engine driving intelligent outcomes.
So as we wrap up today's deep dive into these strategies, we want to leave you with a challenging question to mull over. Think about the current state of your data architecture.
Really picture it.
If an autonomous AI agent were unleashed on your company's data model right now, tonight, without any human there to translate the internal jargon, fix the broken joins, or filter out the bad assumptions, well, what kind of business decisions would it make by tomorrow morning?
That is a fascinating and honestly somewhat terrifying thought experiment for many organizations to confront.
It really puts the stakes into perspective. Until next time, keep optimizing and keep questioning your data.